So I have a simple role this morning. It's just to introduce Jim Schier as our keynote speaker. Jim's been here all week. He's been in the sessions. He's been participating in the working group discussions. And through his resume, you'll see he understands ground systems and space systems and what we're all about. He's NASA's chief architect for the Space Communications and Navigation programs. He's out of NASA headquarters. And really for all of NASA, he's looking at a major part of our overall architecture. But when I look at his resume, his background goes a lot broader, all in space-type systems, both government-wise and commercial. He's worked, obviously, the NASA and international levels on the communication area. At Northrop Grumman, prior to coming to NASA in 2004, he supported re-architecting the NRO's ground system architectures. He led system engineering subcontracts on systems including Iridium and Thuraya, orbital space plane involvement in architecting that. He's been avionics manager and chief systems engineer on Space Station. He's managed flight software development on Milstar, and he's led integration and materials processing experiments on shuttle space lab programs. That's pretty broad reach, from flight software to ground systems to communications. So I think he gets the end-to-end qualified architect qualification stars for that. But he's also been, for this, been well recognized with awards across NASA, the Silver Snoopy, which is one of NASA's highest awards for his work on Space Lab 3, NASA Administrators Group Award for working on space station redesign, another group of them that he's done, but also one that's interesting, the co-recipient of a Brewer Trophy for leadership in support of educational programming and outreach at Smithsonian's Air and Space Museum. So I think he understands the balance, he understands the needs of folks, and I think he really has that end-to-end capability. So Jim's going to talk today about where NASA is headed on resiliency of the large comm systems. Thanks.
Is it on? So I want to start by thanking Dan for inviting me to talk to you today. Just joking, because I'm really very pleased to be here. The ground system is obviously an integral part of the overall system of systems architecture, and we have to focus on that as much as the space architecture. There is no prioritization there. It's an integrated whole. It works together, or the whole thing doesn't work. So what we've been working on at NASA is looking at a system of systems approach that we started studying back in 2012 to see if we could actually migrate to a whole new next generation architecture. We've been operating space communications and navigation architecture since the 1958 beginning of NASA. And for all of that time, we basically had this same fundamental architecture. And the question is that architecture so good that it can't be beat and we should continue doing it for another 50 years? Or does technology offer the ability to go to new architectural paradigms and offer us new and better ways of doing business? So one of the first conclusions that came out of our early studies, looking at the stability of our own space communication networks, was that we do have stable infrastructure. We have both our space networks, our ground networks are ongoing. They have their challenges with obsolescence, but they're fundamentally sound. They are long-lived, and we could envision, therefore, operating the existing networks while we build new architecture in place in parallel and migrate new missions onto new architecture. So we have an opportunity that doesn't come along too often. Once you're in operations and, you know, a sustained pace and you're operating 24/7, 365, you don't often get the chance to contemplate introducing whole new architecture without dragging the anchor of the old architecture around with you. So we've been defining our next generation architecture. It's cleverly named next generation architecture. It's pretty generic at this point. I didn't think that a name was something terribly worth worrying about. And we actually didn't worry about that until the appropriation from Congress last year, where it gave us a requirement to submit a 20-year plan to Congress. And so now we're finalizing that 20-year plan. It's due in about a month from now. And we're going, what do we call this thing? So now we're actually worrying about having to name it, right? So we will come up with something that's not quite so generic, but for the time being, it's still the, you know, NASA's next generation architecture. So what I want to tell you about today is where we're at in defining that, and let you have a chance to ask some questions about what it's done, where we think we're heading. So if we look at the status of the current network, our space network that flies the tracking and data relay satellites, the TDRS satellites, is in excellent shape on the space segment. We launched our last TDRS satellite, TDRS-M, last August. Just a few weeks ago, it turned over and went operational. So our fleet of TDRS satellites is now 10 strong. That gives us 7 operational satellites and 3 on-orbit spares. The weak point on the space network now is actually the ground segment, where we've had the Space Network Ground Segment Sustainment Project going on for a number of years. And that's our OCX. It's our Achilles heel. It's our, you know, this is the one that got away from us, and it's way beyond its budget and its scheduled completion. But it is implementing a whole new architecture that will replace the decades-old architecture at White Sands, New Mexico. Our ground network is operating, continues to add new stations and new capabilities, so that's in fine shape. And I'll talk about a couple of changes with our deep space network as well. So part of the new focus, because we've been working on human exploration for the last few years, is Moon and Mars, right? So we're actually looking at defining lunar network and Mars network as planetary communication networks and ramping up from where we're at with that. So that's been part of the challenge, to think about networks around other planets. We're working on major technology investments, including optical communications. We had our first optical demo, the Lunar Laser Comm demo that flew in 2013 on the LADEE mission. That demonstrated the ability to do 20 megabits per second on the forward link to the moon, 622 megabits per second on the return link from the moon. And we had our first high-definition video broadcast to the moon over that channel. So we're getting ready for our next demo in next year. All right. So let me start by reminding you where we're at with the communication networks at NASA. First of all, the Deep Space Network, we've got 3 ground stations, Canberra, Madrid, and Goldstone, spread around the world, roughly 120 degrees apart, so they can see a 360-degree view of the sky. Combination of 70-meter and 34-meter antennas at each of those ground stations. Next, we have the Space Network, which has its ground stations at Guam and Blossom Point, as well as White Sand, and its fleet of TDRS satellites. At least 2 each over the Atlantic, Pacific, and Indian Oceans, so that we get 360-degree global coverage. And that's how we provide coverage. Each one of our networks now provides service to somewhere between 30 and 40 missions, with a fair amount of overlap between them. Several of the networks provide service to 2 or more networks provide service to the same mission. And then the third, of course, is our ground network, with a variety of ground stations, literally from the Arctic to the Antarctic on all 7 continents. and a combination of NASA-owned stations and commercial service provider capabilities there. So if we look at upgrades that are in progress right now on the Deep Space Network, we're busy building some new 34-meter antennas. Our 70-meter antennas are all literally 50 years old, slightly rusty. They've gone through service life extension. We expect to be able to use them through 2030, roughly. But we're already starting to build out a new set of 34s so that we can ultimately replace the 70s. As we build that, the idea is we build 4 34s, and 4 34s equal the aperture of a 70. And so by arraying antennas, we can equal the performance of a 70 by arraying 4 34s. That is done routinely now, has been done routinely for a couple of decades at the level of, and we can combine 70s and 34s. So the way that we provide service to Voyager, for example, the oldest operating spacecraft, launched in 1977, 40 plus years old, still operating at a distance of over 20 billion kilometers away from Earth, literally more than 3 times farther away than Pluto. And we're still getting a whopping 160 bits per second. Hey, don't snicker, right? 160 bits at 20 billion kilometers is really finding a needle of a signal in a haystack of noise. But we do that by arraying a 70 and a 34 together to be able to talk over that immense distance. And remembering that Voyager is transmitting on a 23-watt transmitter. So one refrigerator light bulb at 20 billion kilometers. It's what we call weak signal processing. The next, in red there, you'll see expansion of the NearEarth Network, where we're adding Ka band capacity. We have new missions, particularly Earth science missions, that are pushing into the multi-gigabit per second range, and so we're going to expand not only the sites, but also the existing sites to add K-band high-rate capability to support those missions. And then the next thing is to refresh the space network capacity, because of those 10 satellites that I mentioned, 4 of them are 22 years old for the youngest at this point, and they are going to be retiring in the next several years. So by the early 20s, we expect to be down from our peak of 10 down to 6 satellites, just enough to cover, with redundancy, Atlantic, Pacific, and Indian Oceans. But at that point, we have to start looking at replenishment of space-based capacity, because the second generation satellites that were launched starting in 2000 will be over 20 years old at that point, and we have to worry about providing continuity of capacity there. So what we're looking at in terms of the next generation is a number of paradigm shifts. So I decided the easiest way to describe the next generation architecture is not by trying to give you a diagram of here's what the architecture is going to look like, but to talk about what are the changes, what are you going to see as this is the way we've always done business, here's the new way that we're going to propose to do business. I think that's a more insightful way to share how we're going to change. So the first and most obvious shift is going to be adding optical communications. I mentioned the LaserCom relay demo that we'll be launching in 2019. We're already working with a number of the programs, including our Human Exploration Program, to go rapidly from that demo into operational optical communication capability by the early 20s. And so then you will have a mix of RF and optical, and you'll be able to take your pick between the competing RF and optical capabilities. They'll overlap in capability a lot, particularly in the early years, but the technology there is continuing to produce improvements so that the optical technology is drawing away from RF, particularly on the space segment, in terms of low size, weight, and power, or SWaP, as well as, we believe, cost. So we think by the mid-20s, we will see optical pull away from RF and leave it in the dust as it becomes the obvious choice for missions. Even small, low-powered missions, even CubeSats, will find optical communications as a compelling technology. The KU band that we've had operational on TDRS for its entire history of over 30 years, NTIA is telling us to get out. So we are planning on the next generation will rely on KA band capability for the high rate communications rather than the KU band. So we'll have KU band capability for the next 20 years out to roughly 2040 with the existing TDRS fleet, but the next gen won't have KU band capability in it. So that's a hole that a lot of our users perceive as, what, you're abandoning KU? No, we're getting kicked out. The next aspect is to think about how we can be more efficient at utilizing the spectrum that we have, as well as the network capacity. So for all of our life, we've basically been operating on the good old, I point my antenna at you and you point your antenna at me, and we've got a link for the duration of our pass or our event. And that works fine. For example, on the International Space Station, they use our 300 megabit per second TDRS link at 300 megabits per second. We got 100% effective utilization of the capacity on that link. On the other hand, Hubble Space Telescope also uses the same TDRS capability, except it talks at a miserable 1 megabit per second, which is 1/3 of 1% of network utilization. So we have this vast variety where missions have been free to choose how they set up their comm and use the network, right? And they don't care about abusing the network as long as they make their mission parameters and mission cost and so on. So we have this wide variety of incredibly low efficiency to perfect efficiency. And we want to set up a scheme where if you need 1 megabit, you get 1 megabit, right? You want to give them the bandwidth that they need, but not give them temporary occupancy of all of the network capacity while they're doing their business. So to do that, we want to go to multiple access capability, and we'll work on techniques to do that. For all of our history, we've been a link layer service provider, right? We specialize on the combining the capabilities on receiving and transmitting to overcome the free space path loss and complete the link. But what we do is we handle bits and we handle space packets, and that's about it, right? If you want to do anything fancier than that, like network layer service, you're on your own. We're going to evolve into being a network service provider. So that'll be, when you look at that in an end-to-end context from either the principal investigator trying to talk to his or her instrument, or the mission controller trying to talk to the spacecraft, it's going to look a whole lot more seamless between the terrestrial infrastructure and the space infrastructure when it's network service end-to-end. The next one is the old cost argument you've heard multiple times this week. We're all being squeezed from a budget standpoint to get more efficient and lower our cost of operations. So things that are manual today, we have to squeeze in the automation to lower our cost. But in the process, that also emphasizes a trend towards autonomy and making the spacecraft itself more capable so that it can operate with less contacts overall with the ground and be more independent of its own mission control. That reduces the number of tracking passes as well as the amount of data that's needed to be exchanged. We've also, and I'll say in this sense, NASA's had too much money. Don't tell my boss I said that. But NASA's big enough that we've built 3 different communication networks. And that means we've got 3 different development teams, 3 different ops teams, and so on. You don't necessarily have to have that. In fact, one of the things that I admire most about ESA is their S-track architecture, which has 35-meter deep space antenna, 15-meter near-Earth antenna, and then on the other side of the antenna, it's pretty much the same processing string and a single integrated infrastructure for S-track. Single scheduling and so forth, whether you're a near Earth or deep space mission. I can't transform our networks into that kind of architecture. I would if I could, but that's a, you can't get there from here kind of problem. But you can certainly admire that in the abstract sense and wish that we could kind of migrate. Well, hey, we are kind of having an opportunity to migrate, so let's think about heading in that direction now. And that's another aspect that will help us in the long run reduce our cost of development and operations. All right, but it's as much focus on automation as it is on autonomy. And in doing that, right, merge the architecture for near-Earth and deep space communications. And the last one was not originally on my list, security. And I was forced to add it as I realized that in communicating the aspects of the architecture across NASA and to partners that we have this situation in the U.S. with our whole of government approach towards security that basically NSA and NIST are working on this, and then they apply it to everybody, and we get it as an agency at the top level. You shall do this security approach, which turns into policies that are inflicted on all of our missions, and I mean inflicted in sort of a pejorative sense, that it isn't applied necessarily with intelligence. And so what I want to do is use a system engineering approach and figure out how to design security bake it in from the beginning, as opposed to willy-nilly applying with NIST compliance and so on, and not necessarily having the most effective, certainly not the most cost-effective approach to security. So realizing that that's a bit of it's not so much the technical challenge there as it is the institutional government mandate approach that we're really challenging there. That's caused me to add that as an additional paradigm shift. So looking at these in a little more detail, the RF and optical case, I mentioned the fact that we're going to launch our LaserComm relay demo in 2019. And we got about 2 years there to do shakedown testing to make sure that it's operational. And then we'll be launching the first user terminal to the International Space Station, or ISS, in 2021, so that we can test out the space-to-space link on that. And about the same time frame, in the 2022-23 time frame, I was just doing emails yesterday with the boss on how we're organizing this. So we're working with the Human Exploration program, which is a vast and a very large part of NASA's budget at this point. If you've seen the president's budget, they're proposing to make it a $10 billion a year effort at this point. So it's out of NASA's $19 billion. That's a pretty big chunk. So the first exploration mission is now scheduled for 2020. That's a launch of the new Space Launch System, the new heavy lift launch vehicle, with the first unmanned Orion crew vehicle, to be followed in 2022 by the first part of the new Deep Space Gateway, which just got renamed to the Lunar Orbital Platform Gateway in the President's budget. And so this will be a small space platform that will be in lunar orbit and will be a place for the Orion to take crew to. And so it'll be two parts to it, two primary purposes. One, it'll be the proving ground for our technologies that we're testing for capabilities that are needed to take humans onto the surface of the moon and onto Mars. And then it becomes the operational gateway, the rendezvous point for building up several elements of a complex multi-element architecture, things that take multiple launches to assemble in space and operate. They'll be assembled at the gateway before pushing off to Mars. So this will be our assembly point and rendezvous point in space. It's also being worked with our international partners as well. So again, it'll be an international gateway. And so we're looking at putting our first optical user terminals on both the Orion crew vehicle and on that gateway system as well. Deep space has its own challenge for optical. And so we're developing a new technology there. Normally your technology for a laser is a laser transmitter and a telescope as a receiver. But when we get into the deep space environment, a telescope isn't good enough. The only way we can get the efficiency to be able to detect this is if we get down to counting single photons. And so the technology for the receiver on the deep space optical is actually using a superconducting nanowire technology that acts as a photon bucket, and we count the individual photons at the right wavelength. And so we're pushing there into extremely high efficiency. High photon efficiency is actually the name of the CCSDS standard that's in development. By efficiency there, we're measuring that in terms of how many bits per photon we can achieve. We're up to 2 bits per photon right now, trying to aim for 10 bits per photon.